Today, we are going to continue our discussion of the macroscopic analysis of circuits, and there are two major topics. One is a brief discussion of real batteries. We've kind of been talking about ideal batteries up to now, but real batteries don't work quite the way ideal batteries work. And then we're going to talk about capacitors in circuits. And that's a very interesting topic because it gives us a window into something that's not equilibrium and not steady state. It's actually the transients. And if we have time, I'd like to show you the movie that shows the detection of surface charge on the surface of a circuit, but I don't know if we're going to have time, so we'll see about that. Okay. So, real batteries. So remember that what we've done so far in our review of our move to the conventional macroscopic discussion of circuits is to define, to group together some microscopic quantities into macroscopic quantities. So we ended up with conductivity, which is a property of the material. It had the symbol sigma, and it was the absolute value of the charge of a mobile charge times the mobile charge density times the mobility of the mobile charges. So basically how good a conductor something is. More mobile charges, the better conductor it is, the more mobility, the faster they move with a given electric field, the better conductor it is. So conductivity is a property of a material, and so it's a property of silver versus gold versus copper versus aluminum. But it doesn't depend on geometry. And we also define a quantity called resistance, something that is much talked about in circuits. And that combined not only the properties of the material, but geometry. And so resistance is a description of a particular object, like a light bulb or a piece of wire. Resistance came out to be defined as the length of the resistive object divided by the conductivity times the cross-sectional area. And it had units of ohms, and the symbol for that was an uppercase Greek omega. And so we found that for a resistor, the current through a resistor was proportional to the potential difference across the resistor divided by the resistance. For as long as we were in an ohmic regime where the resistance doesn't change with the current. And we also wrote loop and node equations for circuits involving power supplies and resistors and whatnot. And we learned some conventional symbols for it. So if we have a circuit that has a battery and a resistor, so this was the battery, and remember that the longer line is the positive terminal of the battery. So this is battery or a power supply in general. This is a resistor. And So writing a loop equation, so it looked like this in the macroscopic, the form, the delta V round trip. Was equal to, we have to choose a path direction. And so if we go this way, we're going from the negative terminal of the battery to the positive. We're going against the field, so we have a positive potential difference. Plus, we neglect the potential difference in the wires because the electric field there is so small compared to the field in the resistor. And so we'd have the potential difference. So this is the potential difference in the battery. This is minus I times R. This is our, from this equation here, our delta V for the potential drop across the resistor. And that's the delta V of the resistor. And that whole thing was equal to 0. And so in this very simple circuit, if we solve our loop equation to get the current, we'd find that the current was equal to the EMF over the resistance. And at least one of you objected to this, in that as we decrease the resistance, so as the resistance goes to 0, so the resistor gets smaller and smaller, it looks like the current should get infinitely large. And that indeed would be a problem, because we would be very surprised if we got infinitely large currents. So what's really going on in a real situation? So this is with an ideal battery. What's an ideal battery? Well, an ideal battery, recall that the way a battery works is that we've got chemical reactions going on. So at the negative end, we have a reduction reaction going on so that electrons are being liberated and they can flow through the wire. At the positive end, we have an oxidation. Whoops, I did it backwards. Oxidation at the negative end and reduction at the positive end, to where the electrons are used up in chemical reactions. An ideal battery means that, and to keep charges balanced, that ions have to be able to diffuse through the goo inside the battery. Well, the ions don't have infinite mobility in the battery. And if we talk about an ideal battery, it means that the ions basically have infinite mobility. But in fact, they have quite finite mobility. So in a real battery, charges have finite mobility. And so that some of the work done by the battery just ends up heating the battery, trying to drag these charges through the battery. And so it acts as if it acts as if there's really some resistance in the battery itself. And so a real battery can be modeled as if it was an ideal battery in series with a resistor that's actually inside the battery. So this whole thing is model as an ideal battery in series with a resistor. And this, and that's not really what it is, okay? I mean, it's the resistance is distributed throughout the whole battery, and it has to do with how slowly the ions can move through it. But this internal resistance is usually symbolized by a lowercase r instead of an uppercase R, and so, and that's called the internal resistance. And so, in a loop equation for a more accurate loop equation for the circuit we drew up here, we'd really have to consider an internal resistance as well. And so here would be our battery, but now we draw this internal resistance. So here's our resistor R, here's our EMF, here's our internal resistance, and this is, again, you know, all lumped together inside the battery. And so a better loop equation would be delta V round trip is equal to the EMF minus the internal resistance of the battery times the current. So that's essentially a potential drop. Some of the energy of the battery gets used up to just get those charges through the battery, minus the current times the resistance of the resistor equals 0. And so what we'd really get is that the current is equal to the EMF divided by the sum of the internal resistance of the battery plus the resistance of the resistor. So how does that play out in the real world? So a fresh D cell, that's the big fat 1.5 volt batteries, D cell, for a 1.5 volt battery has an internal resistance equal to about 1/4 of an ohm. So let's see what would happen if we connected different resistors to the battery. So let's actually make a table. We have what would happen with an ideal battery and a real battery. So suppose we had our resistor R was 100 ohms. Then the ideal battery would give a current of 1.5 volts over 100 ohms. So we'd get 1.5 times 10 to the minus 2 amps. For the real battery, the current would be 1.5 volts over 100.25, or 100 plus 0.25. Which would give us very close to 0.015 amps. It'd be 1.496 times 10 to the minus 2 amps. Okay, for a 10 ohm resistor, for an ideal battery, we'd predict 0.15 amps. And for the real battery, we'd get 1.5 volts over 10 plus 0.25 ohms. And that would give us a 1.463 times 10 to the minus 1 amp. And so that's not also just not going to be a big deal, right? But when we get down to a 1 ohm resistor, a small external resistance, it's not a very good omega, is it? Then for a real battery, we predict 1.5 amps. And for the ideal battery, I mean, for the ideal battery, 1.5 amps. So the real battery, we'd get now it's 1.5 divided by 1.25 ohms. And we would really only get 1.2 amps. And for a short circuit, in which resistance is nearly 0, we'd predict an infinite current for a real battery, but for an ideal battery, but for a real battery, we would, now the only resistance is the internal resistance of the battery, and so we'd actually get about a 6 amp short circuit current, which is basically what we get. So in a problem, if you're not told otherwise, then you can assume that you're analyzing a circuit with with an ideal battery, and you can neglect the internal resistance. However, if you're told about an internal resistance, or you're asked, then you have to actually take that into account. So capacitors. So we talked about capacitors when we talked in chapter 15, actually, we talked about the electric field made by capacitors. But what we're going to talk about today is putting capacitors into circuits. So let's think about what would happen when we put a capacitor into a circuit. So we'll draw this circuit. Here's our battery. And let's put a resistor in, so maybe a light bulb. And then we're going to put a capacitor in the circuit. So this is a resistor, this is a capacitor, initially uncharged. So what do we think is going to happen? Seems like, will the light bulb light? So let's actually see what you think. Will the light bulb one, yes, two, no. Now, so this is a light bulb. Now, there is a battery, but on the other hand, the circuit is open. There's a gap between the plates of the capacitor. And so, do you think the light bulb will light or not? So the opinion is divided, but more of you think the light bulb will light than will not light, but it's by no means so. It's sort of a 60-40 division here. So let's see what actually happens here. So, so what we're going to do is actually try this. And that means we need some equipment. So here's a battery. And Here is a light bulb in a socket. Here's some wires. This thing here is a capacitor. It's kind of it's a special one, as we'll find out, but it's a capacitor. Notice that it's got two wires coming off of it, one presumably connected to the positive plate and one connected to the negative plate. And just to make sure that it's initially uncharged, what we can do is just connect a single wire from one of these connections to one of these wires to the other, to make sure that, okay. So what we're going to do is I practiced this morning, but it's hard because this is all sort of backwards here. So here's our battery. We're going to hook up the red wire goes from the battery to the capacitor. The next red wire goes from the other connection to the capacitor to our light bulb. And then the final wire goes from the light bulb to the other end of the battery. And since what we really want to observe here is the light bulb, let's make sure that's in the camera. Okay, so I'm going to connect the circuit to the battery, and the light bulb does indeed light. So those of you who said it would light were correct, except that it's getting dimmer, and there's only a very tiny little red glow there, and now it's gone. So it actually did light, but it didn't stay lit. It got dimmer and dimmer and dimmer, and then it went out. And now it's still connected to the battery, but nothing's happening. Okay, I wonder what would happen if we take the battery out of the circuit altogether. And so that now all we've got is, we don't need that wire, the light bulb and the capacitor. So what's going to happen when I connect the light bulb to the capacitor without a battery in the circuit? So one is the light bulb is going to light, and two, the light bulb is not going to light. All right. You are very evenly divided on this. So 51-49, essentially 50-50, you say it will light and it won't light. So let's see what happens. So here's the capacitor, which we, oops. So let me remind you that when we did connect when we had the whole circuit connected, the light bulb did light, but then it went out. And the reason I'm doing this again is I noticed that I had actually shorted out this capacitor by letting a contact touch both wires of the capacitor. Okay, so now what we'll do is we'll disconnect the battery away, And we're just going to hook up the light bulb to the capacitor. So here goes. We see that the light bulb is indeed lit, but it's getting dimmer and dimmer. There's a tiny little orange glow here, which, yeah, you can just barely see there. And now it is out. So this observation, so the light bulb actually did light when we connected it to the capacitor after we had connected the capacitor in series with the light bulb in a circuit. So this observation should actually, so would it do that every time, or is it because the battery charged the capacitor? Well, note that, so that's kind of the key question, isn't it? So note that now, I'll just do it again, and the light bulb isn't lighting. So in fact, it's something about the state the capacitor was left in after we had it connected to the battery and the light bulb. So it does seem plausible that the battery would, in fact, have charged the capacitor, right? So let's see if we can make sense of this. In fact, we can actually rule something out, I think, in just thinking about what happened. So here basically is a diagram of this circuit now drawn not schematically, but sort of pictorially, all right? And let's say, so we started out with no charge on the plates of, so here's the battery, here's the capacitor, and there's the light bulb. So we presumably started out with no charge on the plates of the capacitor. So initially Q equals 0. So this is like a little comic strip evolving in time here. So let's think about two things. Let's think about charge on the capacitor plates, and let's think about electron current, just to be very concrete. So this is at time t equals 0. We've just connected the circuit. We saw that the light bulb was definitely lit, but presumably there was no charge on the plates of the capacitor. Now there seem to be two possible things that could happen. So we would definitely have electrons flowing out of the negative plate of the battery. So this is electron current and electrons flowing that way in the circuit. But what happens at the capacitor? It seems like there are two possibilities. One is that electrons just jump across the gap and keep going. And the other is that they don't. They can't jump across the gap. So can electrons jump across the gap? And the answer is they actually cannot, because it actually takes a lot of energy to pull an electron out of a metal. And in fact, many capacitors are designed not with air in between, but with some insulating material like glass or plastic or something like that, even wax paper. Something that's not a conductor. And air is a pretty good insulator. So we'd actually have to ionize air. So we need an extremely high electric field here, or it could even be a vacuum. So here we have an insulator, which could be air or a vacuum. And to make that into a conductor actually requires a very, very, very high electric field, and there's nothing to make that high electric field. So electrons can't jump across the gap, and that's consistent with what we saw when we when we connected the light bulb just to the capacitor alone, right? Because if all that was happening is electrons were jumping across the gap, we never would have accumulated any charge on the plates of the capacitor, and therefore it wouldn't have done anything to the light bulb by itself. So it appears that electrons were not jumping across the gap. Instead, they must have been piling up on this left plate of the capacitor here. And okay, so we start getting electrons piling up on so T equals delta T some small time later. We're starting to get electrons piling up on the negative plate of the capacitor. Well, now these electrons that are piling up on this plate are going to contribute to the electric field everywhere in the circuit. It's no longer just the battery, right? And in particular, the electrons over here on this plate are definitely going to feel the electric field due to the left plate. And so they're going to want to be somewhere else. And so, in fact, they're going to flow off that plate and into the wire, making this plate accumulate a slight positive charge. But it's also the case that having electrons on this capacitor plate makes it harder for electrons to flow onto it, okay? So the electrons, this capacitor is actually, looks like a dipole, right? And it's actually making a dipole, a field outside the dipole here. So we've got E capacitor here, and that means that it's actually going to repel the oncoming electrons in this electron current, which means that this current is going to decrease slightly. So I decreases, and the electric field of the capacitor increases. And so the bulb isn't as bright because these incoming electrons are repelled by the capacitor, and they're slightly attracted to the other side of the capacitor. So the net result is that the electron current decreases. And this keeps going until what? Well, it keeps going until we get to a situation where there's so much charge on the capacitor that now the net electric field in the wires is actually 0. Because E net is going to be the electric field of the battery plus the electric field of the capacitor plus the electric field of the charge on the surface of the wire. And so, in fact, at T equals T plus lots of delta T's, and delta T, the current equals 0, and E net in wires equals 0. Is it like it's storing the reverse of the battery's electric field? It certainly is storing something. It's storing charge, I'd say, and the result is that it produces an electric field that's equal and opposite to the field of the batteries. And the wires, there's of course going to be some charge on the surface of these wires too, although it's actually really instructive to look at a location. It's simplest to look at a location inside the wire, but very near the capacitor, because then, as we saw in that VPython program, the field here in the wire here was due very much to the, it had a big effect from the fringe field of the capacitor. So if you disconnect the capacitor and turn it around, then the bulb would light again. Well, it turned out we didn't have to, so that's exactly what we did, right? We disconnected the capacitor and connected it to the bulb alone. And it turns out we didn't have to turn it around because the light bulb doesn't care which way current flows through it. If you had an LED, it actually matters. Current only flows one way through an LED, and so we might have had to do some turning around. But for a light bulb, it doesn't make any difference. And so let's think about what did happen when we connected the light bulb to what we now know is a charged capacitor. Okay, so we ended up with after the charging phase, we ended up with a lot of charge on the plates of the capacitor. Now this circuit, actually, at the end, when we got right down to it and the current stopped flowing, this circuit was actually at equilibrium. Because E net was 0 and no current was flowing. But there's certainly charge and presumably energy stored in the capacitor. So what we saw here was a transient. We were never really in a true steady state because the current was continually changing. So not a true steady state. Now we've talked about transients, the transients that happen when you bend a wire or when you connect a circuit or whatnot. And we talked about them being very fast, but here we have a mechanism for actually slowing them down so we can watch them. So when we discharged the capacitor, we started out then with, let's see, the positive plate was the right plate. We started out with a lot of charge on the positive plate of the capacitor and a lot of negative charge on the negative plate of the capacitor. And now that's our primary source of charge for the circuit. And so again, we would have some charge on the surface of the wires, which I'm not actually attempting to draw, although maybe I should. So presumably we'd have some negative charge here. We'd have a gradient of charge. And we'd have some positive charge here. And some positive charge here. And some positive charge here. And we need a big gradient across the light bulb because we need a big electric field here. And so we would get electron current flowing electrons. This time electrons would be flowing the other direction, wouldn't they? So we'd have electron current flowing off the negative plate through the bulb and onto the positive plate. Okay, well now we have negative charge flowing onto the positive plate of the capacitor, right? So this is, again, T equals 0. So since we have negative charge flowing onto the positive plate of the capacitor, that's surely going to make the positive plate of the capacitor a little bit less positive. And we have electrons flowing off the negative plate. So we're going to have here less charge, lots of charge. And less charge means a smaller field. And so here we have T equals some short time afterwards, delta T. We've still got electron current flowing here, but it's smaller. So maybe I should make these arrows bigger to show that we have a big current here for starters. So we have a smaller but non-zero current. And finally, we get back to a place where how much charge do we have on the capacitor now? Well, all the charges flowed, all the electrons, excess electrons have flowed off the negative plate and around the circuit. So now we're back to having 0 charge. And that must mean that the electric field everywhere inside these wires is 0 and the bulb is off. So T equals some large, and I equals 0, and Q equals 0. So again, we saw the transient. So let's just try to summarize what we've seen in the form of some graphs, maybe. So let's talk about the charging process. We start out with the capacitor initially uncharged. And if we want to graph the magnitude of the absolute value of the charge on the right plate versus time while it's charging, what would this graph look like? So you said graph 2, which does indeed reflect what we just discussed, right? So what we said was, well, the capacitor was charging here. The capacitor started out uncharged and then got some charge and then finally ended up with a lot of charge. So in fact, the only graph that looks like that is in fact graph 2. Okay. Now, when we started out with the charged capacitor, which we had produced by charging it, we saw that the light bulb also lit, right? So the question here is, which of these graphs describes the current through the circuit as a function of time while the capacitor is now discharging through the light bulb. And you say overwhelmingly and correctly that we did initially have a current when we connected the circuit, and we could tell because the light bulb was bright. But then as the light bulb got dimmer and dimmer, that reflected the fact that the current was decreasing with time. Okay, so how some capacitors are not all capacitors are the same though. So how are capacitors characterized in this macroscopic circuit distribution, circuit description? So capacitors are described in terms of a quantity called capacitance. And its units are farads. I guess actually the units have a small lowercase, and the symbol is F. This is named after the brilliant British physicist Michael Faraday. And so obviously it has something to do with the amount of charge you can get on the plates. So because it's a bigger charge on the plates would give us a bigger electric field. And so that would also give us, if we measured the potential difference between the two plates, it would also give us a bigger potential difference between the plates. So the relationship here is that Q, which is the charge on the positive plate, basically, is proportional to the potential difference across the plate by this quantity C, which is the capacitance. So this is charge on positive plate. This is delta V across the plates. And this is the capacitance. So another way to write this is capacitance is the ratio of the amount of charge on the plates to the potential difference across the plates. And so a farad must be units of a coulomb per coulombs per volt. Well, the transient current of the circuit with only the charge capacitor, is it just the result of built-up surface charges redistributing? There are two things contributing to that current, the field in the wires and in the light bulb that drives that current. One is absolutely surface charge, and the other is the field of the capacitor itself, because we know that a capacitor, the field inside the capacitor doesn't affect any electrons because there are no electrons there to be affected. But we know that there is a field outside the capacitor. Remember, it's called the fringe field. And so it's that fringe field plus the field of the surface charges, which are continually redistributing as the current decreases, that actually drives that current. So it turns out that our favorite energy conservation equation, aka loop equation, also applies to circuits with capacitors in them. So if we have a battery, here's the circuit we were just talking about, a battery, a light bulb, and a capacitor, which is the one we've been using. So we have an EMF, we have some resistance R, we have a capacitor with capacitance C. We can say we know electron current is going to run from the negative pole of the battery on to the bottom plate of the capacitor. But if we talk about conventional current, we'd have these imaginary positive charges flowing off the top plate of the battery through the resistor onto the capacitor. So we'd have a conventional current, capital I, going that way. And so we could write our loop equation The change, the delta V for the round trip is, let's make our loop go that way. So we have the EMF of the battery. Again, we're neglecting the conducting wire, the connecting wires, because they're so thick that they have such a small field in them that they don't matter much. And we have the potential difference across the resistor. And now we have so this is change potential difference across the battery. This is the potential difference across the resistor. Now we need the potential difference across the capacitor. And we can write that in terms of this capacitance. So we can write, since Q is C delta V, we can write delta V across the capacitor as just the amount of charge on on one plate divided by the capacitance equals 0. And we know something about at least the final state. So this is changing as the circuit's running. Okay, all these values, the capacitance isn't changing, but the current's changing and the amount of charge are changing. So we have a lot of changing quantities in this loop, but it's true at any instant. I mean, this is still valid at any instant, but we'd kind of like to tease out the time dependence of this. We'd like to see if we can understand, we can write this in a way that we actually see the time dependence, right? Now the final state is easy because it's equilibrium. So we have EMF minus Ri minus Q over C equals 0, but in the final state, I is 0. But in general, at other times, while running, we have the EMF minus Ri minus Q over C equals 0. So at any particular instant, the current would be equal to EMF minus Q over C, the whole thing divided by R, or EMF over R minus Q over RC. Well, the current is just actually the rate of change of the amount of charge on the plate of the capacitor, because the number of electrons per second, the number of coulombs per second that flow onto there is in fact the change per second in the charge on the capacitor. So we can rearrange this to get dq. And so current is equal to that, which is equal to EMF over R minus Q over C. So the amount of charge flowing on in one time interval, we can write it as delta Q in 1 dt, delta T. Delta Q is equal to the EMF over R minus Q over C times delta T. And that looks like something we can actually do iteratively. So we could actually write a little VPython program to just, so we'd say, we'd have a loop. So we'd start out with Q equals 0, and we'd have a loop where while well, something. T is less than T max. We'd have Q is, so we'd have dq is the EMF over R minus, oops, thank you, Q over CR times delta T, and then Q is Q plus delta Q, and T is T plus delta T, and then we loop, right? Thank you, Hunter. So let's just see what that looks like. Okay, so here is a GlowScript program that for a circuit like the one we used, in fact, there's a 40 ohms is about the resistance of that particular light bulb that I was using when it's hot. Here I'm using a 1.5 farad capacitor. This capacitor is actually, what does it say? I thought it was 1, but it may actually be a 1.5 farad capacitor. It is 1. This is a 1 farad capacitor, okay? And this is with 2 batteries, so 3 volts. We can change that if we want. And here we're just going to have a couple of graphs. We're going to graph charge on the capacitor, and we're going to graph current. And so we start out with T equals 0. We take a dt. We have Q equals 0, and then this should look familiar. So here's our dq. So EMF minus Q over C times dt, the whole thing divided by R. Q is Q plus dq, and then we plot Q, and to get the current, we just divide dq by dt. So I is, okay. And so what this predicts is, okay, so the left graph is Q versus T. The right graph is current versus time. And we see that indeed the charge builds up really fast at first, but this is pretty nonlinear, and then as its charge starts to build up, it builds up slower and slower and slower and slower until it finally gets to some value that really doesn't seem to change. And likewise, there's a big current, 0.08 amps in this case, and coming down fairly fast to basically in the end 0. Now notice that there would be a huge amount. If we use 2 batteries and a 1.5 farad capacitor, we would end up with 4.5 coulombs of charge on the plate of that capacitor. And in fact, it's a 1 farad capacitor, so it would be a little bit less. In fact, we could change the program to make it a 1 farad capacitor. And we'll run this, and we find that it predicts, not surprisingly, 3 coulombs of charge. And that's a huge, huge charge, right? Because the charge on 1 electron is 10 to the minus 19 coulombs. Now, this is a very special kind of capacitor. Most capacitors that are used in ordinary circuits have capacitances on the order of millifarads or microfarads. This thing is a special capacitor called a supercap. And it has, the reason it can accumulate so much charge is that, in fact, the gap is very, 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 very small. The gap is on the order of an atomic distance. And so it's not really 2 plates curled up. The normal capacitors really do have, if you cut one in half, you'll find two like strips of aluminum foil with a piece of wax paper between them, all rolled up. So really, they do have plates, and these are used for things like powering a computer if there's an instantaneous fluctuation in power to the computer, for example. So let's see if we could do this analytically. So we clearly, if we do it numerically, we clearly can get the dependence that we get things that reflect what we observe. But this turns out to be a case in which we can actually do this analytically. And so the graph of current versus time that we just saw. So when we did it analytically, we got the graph of current versus time that kind of looked like that. Does that suggest a function to you? It does indeed. Derek is right. It really does look like an exponential, and exponentials turn out to be the function that characterizes many physical processes and biological processes too. So exponentials turn out to be. So let's guess. So one way to solve it, so we have this, so we could guess here, and guessing is actually a legitimate way to solve differential equations, that the current is going to be some sort of exponential. So it has some initial value, I0, and then it will decay exponentially so that it's e to the minus some constant. Let's see, we can't use C because that's capacitance. So let's use alpha t, where alpha is a constant. So if you take anything away, take away exponentials here. And so what we're going to do is plug this into our equation from up here. So here's our equation. We'll copy that. I is dq dt, which is equal to, okay, so here's our equation from before. So let's differentiate. What would happen if we differentiated this? So if we took di dt, that would be equal to the derivative of EMF over R minus Q over C times R. Well, EMF over R is a constant, so that goes away. And so we end up with a minus 1 over RC times dq dt, which is equal to d. So we have, which is a minus 1 over RC times I, because I is dq dt. So that again suggests an exponential, because an exponential is basically its own derivative, because this is constant. So let's try our guess. So we have di dt equals d dt of I0 e to the minus alpha t, which is equal to a minus alpha I0 e to the minus alpha t, which is equal to a minus alpha times I. So we've ended up with here, minus 1 over RC times current is equal to a minus alpha times current, and that's true if alpha equals 1 over the resistance times the capacitance. Now this resistance times capacitance thing is called so this thing RC is called the time constant of a circuit. And so we've ended up with the current in a circuit is equal to the initial current, which is just the EMF over the resistance, because at that point there's no charge on the capacitor, times e to the minus t over RC over this time constant for a circuit of this kind. And that does in fact give us this lovely exponential decay. That's exactly what we saw in our computer simulation. And what does this time constant mean physically? Well, if t equals this time constant RC, then we have e to the minus RC over RC, which is e to the minus 1, which is 1 over e, which is 0.37. So in this time, in a time RC, I decays to 0.37 of its initial value. So we get down to here, and that t equals RC. So for our circuit, so RC is equal to, well, we had in the circuit that we actually looked at, so we had a 1.5 volt battery, we had a 40 ohm bulb, a 1 farad capacitor. So RC is equal to about 40 seconds. So in about 40 seconds, the current had decreased to about 37% of its original value. And that actually was small enough so that the light bulb actually wasn't lighting anymore, even though a little current was probably still flowing. So what did you learn about capacitors and circuits in chat?